Information theory provides a mathematical framework for quantifying communication. This tutorial explores its core concepts, focusing on three fundamental questions. Quantifying information. How can we describe and measure the amount of information we get from a signal? Efficient encoding. How can we efficiently encode data to store or transmit it using the minimum possible space? Noisy communication. How do we communicate reliably when the channel is noisy and might corrupt the message? Information is tied to unpredictability. A completely predictable message contains no new information. The surprise of an event is a way to measure this unpredictability. It's defined by a few common-sense axioms. Surprise depends continuously on an event's probability. More likely events are less surprising, decreasing in probability. The surprise of two independent events happening is the sum of their individual surprises. The only function that satisfies these properties is the negative logarithm of the probability. The unit of surprise and entropy is a bit when using base 2 logarithm. While surprise applies to a single outcome, entropy measures the average surprise of a random variable over all its possible outcomes. It quantifies the total uncertainty of the system. For a discrete random variable x with possible outcomes and a probability mass function, we can algorithmically describe entropy with the following. This can also be seen as the expected value of the surprise. By convention, 0 log 0 is equal to 0, since an event with 0 probability never occurs and shouldn't contribute to the surprise. The example takes the probability of a coin with two outcomes, heads or tails. As we adjust the probability of heads, there becomes a probability curve that can show its relation to entropy. Now let's get into divergence and mutual information. KL divergence, or relative entropy, measures how one probability distribution P diverges from second expected probability distribution Q. It's a measure of the distance between two distributions. Imagine a three-sided die. Define two different probability distributions, P and Q, for the outcomes 1, 2, 3, and see how they differ. Mutual information between two random variables measures the reduction in uncertainty about each other. The KL divergence between the joint distribution and the product leads to more intuitive information regarding their entropies. If X and Y are independent, and their mutual information is 0, if they are perfectly correlated, knowing one completely determines the other. With a probability table of known probabilities, we can deduce all other information on entropy from a system. Be sure to check out the GitHub for the code of this tutorial, and continue on with other machine learning related short tutorials by checking out the playlist.